Great. Can you see me? Or can you
Yes,
hear me?
yes. Yeah. We can see your screen also.
Wonderful. Well, thank you so much. First, I wanted to say thanks, Sunil, and also Fazil for inviting me to join you. This has been a wonderful afternoon so far. The other presenters did a great job, learning lots, and in fact, I've been changing my presentation a bit to be a bit more responsive to the flow of the dialogue. And before I get started, a quick safety tip, since we're all sitting for an hour now. Just check how you're sitting, make sure you're seated up, get up and walk around if you can hear me during the presentation. Very good. I see Driver stretching right now. That's fantastic. So I'm going to go through a quick framework and then talk a little bit about an example of how we're approaching this issue of resilient One Water digital innovation, and then end with some observations based on this morning's conversation. I'm going to start off, if you can see, with just a kind of brief statement of the problem that we're trying to solve here at Xylem, which is that we see stakeholders in the water ecosystem struggling because there's more work to do. There's obviously environmental change, there's demographic change, there's regulatory change. Obviously things like COVID have led to the need to do that in a safer way, and also with less money given some of the economic fallout and the recession that we're now in. And so our goal is to partner with clients across the water cycle to enable digital transformation that helps the water industry operate more effectively, safely, and affordably. And key to that approach is thinking about something we call decision intelligence, which I think is very linked to many of the models we've seen this morning or this afternoon, which is this basic premise that smart water isn't just about sensors. It's about using sensing, prediction, and decision support and analytics in order to drive action and improve decision-making. And the core thesis is that by driving stacks of technologies that are oriented around specific operational and financial outcomes, we can make significant improvements in the resilience of the industry. So if I go to the next page, COVID has been really interesting because in the first phase of the COVID crisis, and we're not out of it yet by any means, what we saw was a huge amount of concern about the operational resilience of water utilities, particularly because we all needed to wash our hands, and it's hard to do that if you don't have clean water. And then you were flushing all of these wipes down the toilet, not you personally, and then people were having all these jammed up pipes and pumps to deal with. And so the critical piece around operational resilience is that, first of all, even though most utilities managed to make it through the crisis, those who had made investments in cyber, physical, and digital systems had a much easier time of the last couple of months. And that's true because investments in monitoring, control, optimization, and automation paid huge dividends when part of the objective function around operational resilience was to have fewer people on site. We heard from some utilities that were saying that they needed to have people go out and physically visit pumps several times a day just to make sure that they weren't clogging, whereas other utilities were able to look at the sensing data that was coming out of it and alert for problems that were forming. That difference in workflow is huge when you're trying to keep people safe at home. Similarly, with meter reading, utilities that had made investments in advanced metering infrastructure found it a lot easier to collect data and revenue than utilities that had to estimate because people didn't want meter readers at home or when their meter reader populations got sick. So digital clearly has a payoff with respect to operational resilience. But the really interesting thing for us was that the phase that we're exiting now, which is around the immediate operational crisis, is now being replaced by something even more serious, which is a financial resilience crisis.
Albert, can you interrupt? Can you put one comment I got in the chat? Can you put it in presentation mode?
Oh yeah, I can do that for sure.
Great, thanks.
So with respect to financial resilience, one of the things that we saw is you've all read the NOC1 AWA reports about 15 to 20% reductions in top line revenue coming from either delinquencies or rate increase deferrals or just the collapse of commercial industrial revenue in certain utilities. And so then the question is, how do we safely increase cash flow, either in the operating budget or the capital budget? And the key word there is safely, because you can obviously cut your way to cash flow savings in ways that don't advance the mission of public health or environmental sustainability. And so part of the role of these decision support systems is to guide decision-making that allows us to increase operating cash flow and lower capital expense, but doing so while maintaining policy objectives around environmental quality and public health. And so what I want to talk about today is this approach of using sensing, prediction, and action, right? This decision intelligence stack to drive improvements in financial and operational resilience across the water cycle. I'm going to talk in the first instance about an example by a company that we acquired 3 years ago called Mnet, Luis, the founder, is on our call and is one of the smartest people I've ever met. The core thesis that he brought to the industry a few years ago, working, I think, with many of the people on this call, is about deploying sensor networks, using that real-time data to improve hydraulic modeling. You can create digital twins using artificial intelligence that enable real-time control, thereby making better use of existing assets and achieving superior environmental outcomes at dramatically lower cost. And so this is a kind of stack here that demonstrates how that company, and which is now part of our company, has demonstrated how to use data, not just to instrument and turn on the lights in physical systems, but to use it to drive improved operational and financial outcomes. So in South Bend, Indiana, just to give you a specific case example, some of you may be familiar with, the implementation of this decision intelligence stack was able during a period where rainfall doubled from 31 inches a year to 60 inches a year to reduce overflows by about 70%, saving on a net basis about $500 million of capital investment and infrastructure. And those are the kinds of proof points now in about 20 different cities around the United States, where the application of decision intelligence can enable significant savings in capital expenditure, but also in operating resilience. So when you create a digital twin using artificial intelligence, a hydraulic model, and real-time sensing, you're able to use that data in a lot of different ways to drive decision-making. And so in the first instance, you can automate the process of identifying, quantifying, and locating blockages in the sewer network using flow data and modeling. And so this is one example of locating a couple of tons of grit and hair, which would be particularly useful right now, using the same sensor network that was used to manage the volumetric problem of wet weather in Indiana. It can also, by creating this digital twin, enable the identification of things like inflow and filtration, which obviously has a significant downstream impact in terms of energy efficiency and the management of the treatment plant. So that same network, whether you're in a combined or a sanitary sewer network, is able to tell you things about the performance of that infrastructure using, again, the same basic decision intelligence stack of a well-selected sensor network, a hydraulic model that is adapted through artificial intelligence, and the creation of smart decision pathways that enable better operational control. From a financial perspective, what that allows you to do is to simulate many, many different potential combinations of infrastructure that will meet your policy objectives over time. And that's how ultimately, by working with the local community in South Bend, the team was able to identify a much lower cost mix of infrastructure investments that met the same policy objective from an environmental perspective at significantly lower cost. And I think if I step back from that example around wastewater, I think the key insight is that what data analytics and smart infrastructure actually enable are the freeing up of degrees of freedom that can significantly improve the range of choices for operating and environmental variables. So on the left-hand side, this is a scatter plot that's been generated in a wastewater treatment plant by a very similar approach. We have a set of applications that basically develop a digital twin of a wastewater treatment plant, enabling you to run simulations in real time and ultimately pick optimal control points that tell you how to operate equipment within the treatment plant in a way that meets certain effluent quality requirements at the lowest specific energy input. And so by running those simulations, you're able to create a performance curve, which is typically a significant improvement both in environmental and in economic terms over manual set points that are generated by even trained operators. In the middle, another application and use case around safely reducing capital expenditure, again, in the theme of cash flow improvement while maintaining specific levels of service. This comes exactly back to what we heard about in the prior conversations, which is by using data analytics around pipe history, around break history, but also linking that to hydraulic models and construction planning, you can find ways to more efficiently allocate limited spending on pipe replacement to either maintain the same break rate, dramatically reduce it, or some mixture of saving money and improving the overall level of service by reducing break rates. And that can be done by combining those approaches to predicting the performance of infrastructure with other application layers that enable you to cluster things to make it easier from a workflow perspective to schedule and execute engineering projects in the real world. And so that's another example of how basically by modeling out a potential range of frontiers based on data, it creates more degrees of freedom with respect to that balance between economic and policy objectives. And on the right-hand side, this is kind of a nifty example with respect to wastewater pumping. Another big issue right now has clearly been that wet wells are getting clogged up. They're having overflows. They're creating problems in a number of municipalities around the world. And one of the things that we've been able to do is to infuse the wastewater pump with artificial intelligence so that the variable speed drive and the operation of the pump station is informed by the conditions and the actual hydraulics of the pump as it's spinning. And what that enables is for a much smaller number of pump models and sizes to operate not on a pump curve, but in a pump field, thereby enabling a pump station or a set of pump stations to be served by a more resilient and more effective limited set of models, thereby saving on infrastructure expense, on inventory, and improving energy efficiency. So the reason I lay this all out is to say that there are huge opportunities with respect to improving the resilience, both operationally and financially, of utilities in the industry. What I want to try to spark a conversation about in the breakout sessions is, what problem are we trying to solve through this center and through this exercise? Because not everything falls in the domain of research. Some of it is about solving a problem of technology commercialization and adoption in any market where there are barriers to the adoption of even proven innovation. And so one of the questions that I want to ask is our focus around trying to solve unmet needs in the industry from a research and development perspective to try to accelerate technology and innovation adoption so that we get past innovators and early adopters to the chasm, through the chasm, to large-scale adoption of innovations that can save people money and improve the level of service? And what role do each of these stakeholders in this honeycomb diagram have to play? Utilities, venture firms, technology firms, NGOs, startups, and universities, because all of them have a different role to play at different parts in this cycle. And I would be curious to see where research needs to happen versus where effort around technology diffusion and de-risking from the perceived risk perspective, our collaboration can support. And this is my last slide so that we can cut straight to the discussion, which is some of the inhibitors and challenges that the industry still needs to solve. First, workflows and people. I missed the last session around workforce, and so I'm not going to speak a lot about this because I know the team has probably already covered much of this in the past. Cybersecurity is an area of emerging need where really understanding the sources of risk, whether it's in training or whether it's in infrastructure systems or whether it's in connectivity, those are all questions that I think the industry would like to hear more about. Interoperability has already been touched on already. I think that's clearly an area that acts as a barrier to the full potential and realization of economic and operational benefit. But there are two other things that I think research and development could really help us with. One is market failures. There's a lot of research, I think, that needs to be done around areas that the industry isn't really touching, particularly around the interface between utilities, agriculture, and the natural ecosystem, where I think there's just some really interesting policy research, technology research, and kind of a fusion of the two, where there are some market failures that won't get addressed given existing funding models. And then in terms of physics, I loved some of the work that Jovito was describing around battery-free operations and sensor networks that are able to connect in new topologies, because all of those things I think will help expand the boundary conditions and frontier for new innovations that will then fuel a new cycle of improvement in capital and operating cost. And with that, I'll stop.